The bias-variance trade-off describes the balancing act every machine learning model faces. Make the model too simple, and it misses the overall trend. Make it too complex, and it starts memorizing the training data. And our goal isn't to memorize the training data. It's to identify the true trend in the data, so that our model can predict well on new data that it has never seen. Models that are too simple have high bias. They make strong assumptions about the data, so they consistently miss important patterns, a problem called underfitting. It's called bias because the errors are systematic. Train it on different data, and it makes the same kinds of mistakes. On the other hand, models that are too complex have high variance. They're flexible enough to learn the noise instead of just the signal, causing a problem called overfitting. It's called variance because small changes in the training data can produce very different models, and therefore very different predictions. But how does model complexity affect error? As a model becomes more flexible, its training error almost always decreases because it can fit the data more closely. But the test error tells a different story. It first falls as the model captures the real patterns, but eventually rises again as overfitting takes over. So we know what the trade-off looks like. But why does this happen? Mathematically, prediction error can be broken into three parts: bias squared, variance, and irreducible noise. Bias squared comes from overly simple assumptions. Variance comes from the model being too sensitive to the training data. And irreducible noise is randomness no model can remove. The sum of these components is the total test error, and the lowest point on this test error curve is where these errors balance, flexible enough to learn the signal, but not so flexible it memorizes the noise. The core idea is simple. Increasing model flexibility generally reduces bias, but increases variance. Good machine learning is about finding the balance between the two.